Hello, my name is Qihang Chen, an undergraduate student in Tsinghua University. It's my honor here to present our work, Fingers, Exploiting Fine-Grained Parallelism in Graph-Mining Accelerators. Beyond traditional graph analytics such as PageRank and single-source shortest path, graph mining is an emerging problem that locates all the subgraphs isomorphic to the given pattern of interest. For example, two subgraphs are isomorphic to the pattern in the example graph. They are called embeddings. Graph mining has various applications in reality. Bioinformatics and cheminformatics discovers 3D motifs in proteins, genes, and chemical compounds. Social science identifies dense cliques among groups of people through social network connections. However, due to the superlinear growth of possible embeddings with the pattern size, graph mining is fundamentally much more compute and memory intensive than traditional graph algorithms, making it necessary to incorporate specialized software and hardware designs. The state-of-the-art graph mining systems use the so-called pattern-aware algorithm. We'll use the tailed triangle pattern with 4 vertices as an example to illustrate this algorithm. The high-level idea is to gradually build up the subgraph by adding one vertex at a time and maintaining the pattern, for example, in the order of U1, U2, U3, U4. Each vertex in the input graph could be chosen as the initial vertex, and a tree-style search will be executed. We will first introduce a successful searching process. When we start from vertex 2 as U1, we first find all its neighbors as the candidate for U2 at the first level. One of the branches lead to subgraph 2, 3. For the next level of U3, we notice U3 must be a neighbor of both U1 and U2, so we take a set intersection of the neighbors, which results in only one vertex, 1. Meanwhile, we also calculate the partial results for the candidate vertex set for U4, which is connected only to U1 but not U2, so we do a set subtraction, resulting in a set of 2 vertices, 4 and 5. This can be done in parallel with the extension of U3. Finally, we use the value of U3, which is vertex 1, to finalize the above partial candidate set of U4 and complete the subgraphs. 2, 3, 1, 4 and 2, 3, 1, 5 are the 2 final valid embeddings. From the above example, we can observe that the key operation in the search are set, intersection, and subtraction. Not all branches in the search tree will result in valid embeddings. For example, extending from 2, 1 will find vertex 3 as U3, which in fact is the same subgraph as before when we extending 1 from 2, 3. So this branch should be pruned by applying certain restrictions to break the symmetry. Such pruning is determined by the compiler and orthogonal to our design, so we do not explain them in details. On the other hand, extending from 2,4 or 2,5 will not find any vertex which can match U3, and exploration on this branch will be early stopped. Due to the high computation demands, graph mining has been benefited from hardware acceleration. Existing graph mining accelerators merely exploit coarse-grained parallelism, which comes from the independent tasks starting from different initial root vertices. However, this has several inefficiencies. First, the search tree is usually traversed in a depth-first manner, which is intrinsically serial, and the dependencies between the tree levels would cause long memory access stalls and underutilization of compute resources. Second, chip area is dominated by complex hardware modules for scheduling tree search and caching data, while the actual compute units for set operations are small. Third, real-world graphs with power law distributions may also result in load imbalance, which challenges the effectiveness of simple parallelization approaches. To further improve efficiency, in this work, we additionally exploited multiple levels of fine-grained parallelism to parallelize the search within each tree. First, it enables us to discover more parallel tasks to schedule. Thus, we may execute ready tasks first to hide memory stalls. Second, we can use more parallelly executing compute units in each processing element to amortize the cost induced by control units and caches. Third, we are able to achieve higher single-thread performance to maintain good performance even if we are faced with load imbalance. We will first summarize the 3 levels of fine-grained parallelism in pattern-aware graph mining, as well as the benefits and challenges to exploit them in hardware. The first one is branch-level parallelism. We can enable parallel exploration of different branches in a search tree, such as extending subgraphs 2.1 and 2.3 in parallel in the previous example. This effectively converts a depth-first search into breadth-first. The actual order of exploration is shown in the right side, where we will choose some number of branches to explore in each level and sequentially explore the generated subtrees. Besides extra parallelization opportunities, we further identified an opportunity in hardware accelerators that it enables more available tasks to execute, tolerating memory access latencies similar to multi-threading. A challenge induced by branch-level parallelism is that besides reducing data dependency and providing more parallelism, exploring too many branches in parallel may greatly increase the intermediate data size. We therefore need to balance those effects. The second one is set-level parallelism. Recall that at each level of the search tree, we calculate not only the candidate set of vertices for the immediate next level, but also the partial results for candidate sets of other levels further down the tree. Therefore, there are multiple sets that can be updated in parallel. All these sets use the new vertex neighbor list, which is a long set, to update the candidate sets, which are short sets. Besides offering more independent workloads for parallel scheduling, set-level parallelism also provides chance to reuse the same long set. The elements in the long set is loaded to PE sequentially and fully reused to avoid cache stretching when the neighbor list is too large. However, we need to overcome some challenges. First, depending on how the vertex is connected to the ancestors, the set updates can be either intersection, subjection, or anti-subjection. Our hardware needs to deal with each of them in a uniform and simple way. Second, the degree of set-level parallelism is usually limited, especially in deeper levels where fewer candidate sets remain. This requires flexible resource allocation for higher utilization. The third one is segment-level parallelism. For each individual set operation, we can divide the two input sets each into multiple segments of distinct ranges, apply the operation to each pair of the overlapped segments in parallel, and finally aggregate the results. We discovered that in this way, we have the opportunity to divide each set operation into multiple smaller tasks with similar load, which helps achieving better load balance in hardware. The challenge is how to find an effective strategy to pair the segments to achieve load balance and aggregate the results while preserving correctness. Next, we build a hardware accelerator, fingers, based on the levels of parallelism we have just introduced. The high-level architecture utilizes coarse-grained parallelism across PEs. Our key innovations reside in each PE, where we further utilize fine-grained parallelism. We define a task as a procedure to operate all short sets with a long set at some tree level. In this way, branch-level parallelism is among tasks, and we schedule the order of task execution. Set and segment-level parallelism are within a task, where we use a set of IUs for parallel processing set operations. To achieve this, we add a task divider to divide tasks into segments in front of IUs and a result collector to collect results and aggregate them after set operations. To enable branch-level parallelism and hide memory latency, we maintain just the right amount of available tasks. Our scheduling is related to contents in the cache. We gather a small number of tasks spawned from the same parent task as a task group, whose size is also the degree of branch-level parallelism, chosen to fully utilize the hardware while preventing too large intermediate data. The tasks in a group are popped from the stack together. We first execute those tasks whose input neighbor lists are already in the shared cache by simply issue all tasks to the cache. In the shown example, the task group contains 2, 5, 7, 8. Hits, such as 2 in the example, return immediately to resume the corresponding tasks, while misses, like 5, cause the tasks to wait until fetched from memory. Other hits, such as 7, can surpass the miss to hide memory latency. In this way, we may get enough tasks to execute before we finish handling the misses. To distribute the multiple set operations in a task to the multiple IUs in the PE, we need to find overlapped long and short segments to efficiently pair them together. The first element of each segment are extracted as head. The long heads are organized as a binary tree in hardware, and each short head is streamed in to compare with them and get the corresponding position within the sorted long heads. We use this position to update a load table, which stores the statistics of paired long and short segments. These loads are then pruned and balanced and finally stored into a task table, which records the long segment index and the range of the paired short segments for each IU. The IUs will execute based on the task table. For set operation, since we need a unified and simple way to deal with intersection, subtraction, and anti-subtraction, we always compute the intersection of two input segments on an IU regardless of the required operation, using a simple compare unit that streams in the two input lists similar to previous work. The results are stored as a bit vector with the same length as the long segment, with different meanings for different operations. For intersection, we need to record bit I as 1 if element I in long segment is overlapped with some element in a short segment. Those elements in long segment mapping to 1s are the results. For subtraction, we need to record according to the short segment and take those zeros. The hardware will recognize 2 and 8 are in both sets and output bit 1 at those positions. When we recover the results, only 5 corresponds to 0 in bit vector and should be included in the result set. Anti-subtraction follows the same ideas, and the correctness of the rules can be easily verified. When collecting results from the IUs, the result collector sequentially receives the bit vector. If the current segment matches with the same long segment as the previous one, we need to aggregate the two bit vectors with bitwise OR. For intersection, we union the ones in the two separately computed results with bitwise OR. For subtraction, we intersect the 0 bits, also with bitwise OR. The bit vector and its associated segments from each IU will be translated back to list representation. Finally, we will show our experimental results. We implemented all the newly added components in Verilog and synthesized in 28 nanometers. The area of each key component is shown in the upright table. In total, the PE area of our design is less than twice of the PE area of our baseline FlexMiner, the current state-of-the-art. We also built a cycle-accurate simulator using C++ to evaluate the performance with 7 commonly used patterns on 6 real-world graphs shown in the downright table. We first compared the single PE performance between Fingers and FlexMiner. The Fingers PE outperforms the FlexMiner PE by 6.2 times on average and up to 13.2 times over 7 patterns and 6 graphs, while using only less than 2 times area, which shows that exploiting fine-grained parallelism within each PE can indeed greatly improve the performance. Click counting does not have set-level parallelism, as the candidate vertex sets for all future levels are always identical, leading to low speedup. In other patterns, subtraction or anti-subtraction produce large sets and result in high parallelism and good performance. 3 motifs is better than triangle counting since it can be parallelized in a similar way to set-level parallelism. We next demonstrate the full system performance improvements of Fingers over FlexMiner with additional coarse-grained parallelism at the PE level. We compare a 20 PE Fingers chip with a 40 PE FlexMiner chip for an ISO area evaluation. Overall, Fingers achieves on average 2.8 times and up to 8.9 times speedup over the baseline. The impact of different graphs becomes more significant. Graph AS and MI can fit in the cache, so the performance is not bounded by memory latency. YO and PA are sparse. Their memory access cannot be fully hidden by computation, leading to limited speedups. LJ and OR are relatively dense. They have higher speedups due to massive parallelism. In conclusion, we identified 3 levels of fine-grained parallelism in graph mining and discovered their potential benefits when applied to hardware. We present a novel graph mining accelerator, Fingers, which exploits 3 levels of fine-grained parallelism and achieved up to 8.9 times performance improvement at the same chip area compared with the state-of-the-art baseline and only utilizes coarse-grained parallelism. Thanks for listening, and now I'm happy to take any questions.